Okay, so we spent some time talking about what sequential circuits are in general, and then we moved on to a very simple sequential circuit, the SR latch. Showed how that was able to produce a present state and next state to create some kind of memory element. And then we showed how to take that SR latch and make it into a better memory element, the D flip-flop, by adding extra gates to it. These extra gates then allowed the D flip-flop to be edge sensitive instead of level sensitive, which makes it a better circuit, less susceptible to noise. So we did talk about the D flip-flop, but now we're going to talk about two other common flip-flops used in digital design, the T flip-flop and the JK flip-flop. So right here what I have on the screen is the block diagram, the present state next state table, and the excitation table for the T flip-flop. So here's our T flip-flop. Like the D flip-flop, it has the input, an input T. The D flip-flop has the input D. It has the clock because it's edge sensitive, and it has the output Q and Q naught. So here is the present state next state table of the T flip-flop, and it's called a T flip-flop because T stands for toggle. So when T is 0, that means Q should just, or Q next state, Q plus, should be whatever Q is. It's not going to toggle Q. But when T is 1, that means yes, toggle. So here Q is 0, so the next state is 1 because it toggled or flipped the bit from 0 to a 1. Here T is 1 and Q is 1, so it says yes, toggle. Q is 1, so Q plus is going to be a 0. We can write the equation for Q plus. These equations are called characteristic equations. So Q plus is equal to T exclusive OR Q. As you can see here, this is the exclusive OR function. We're having just one 1 or an odd number of 1s gives you a 1, otherwise you get 0. If we write this in the excitation table form, we get from 0 to 0 when toggle is 0. We get from 0 to 1 when the toggle is 1 because we have to toggle to get there. We get from 1 to 0 when the toggle is 1, and we get from 1 to 1 when the toggle is 0 because we don't toggle to get there. So you can easily, as I forgot to mention with the D flip-flop, you can easily go from your excitation table to draw out a state diagram. So let's just go ahead and do that for the T flip-flop for practice. I'll pull up the bamboo paper. Okay, so for practice we're going to have our two states for the T flip-flop. We have the Q equals 0 state and the Q equals 1 state. So if we're going to stay in Q equals 0, what is T going to be? T is going to be 0, so we're going to write T naught. If we're going to go from 0 to 1, that's going to cause us to need a T. If we're going to go from 1 to 0, we need a T. And if we're going to stay in Q equals 1, we're going to need T naught. So there is our state diagram for the T flip-flop, which can be easily drawn from looking at the excitation table. Okay, so let's see how to use this T flip-flop in practice. Here we have our clock and our T input, and we're going to see what Q does. So in this case, we have, again, we evaluate at the rising edge of the clock. We can have some problems where we evaluate at the falling edge of the clock, but right now we're doing the rising edge of the clock. Q starts out as 1. So at the rising edge of the clock, T is 1, which means toggle. So whatever Q was, it's going to be the opposite. So Q was a 1, so it's going to become a 0. Now we hold until the next rising edge of the clock. T is 1, so yes, toggle. So it becomes from 0 to a 1. At the next rising edge, T is 0, which means don't toggle, which means just hold whatever Q was. So Q was 1, it stays 1. At this fourth rising edge, T is a 1, so yes, toggle. We're going to flip from 1 to 0. We hold the 0 at the next edge. T is 1. That means yes, toggle, so Q goes up. That's how a T flip-flop works. Now let's look at the JK flip-flop. And nobody knows, if you read the text as well, what JK actually stands for, but it looks very similar to how an SR latch works. So here is the block diagram, the present state next state table, and the excitation equation for the JK flip-flop. So again, it looks very similar to the SR latch, where the 0, 0 condition is the hold condition, where Q next state is the same as Q. Then the 0, 1 condition, where K is 1, this is the clear condition. So I remember this by thinking K for clear. It has the same sound as a C does for clear. So if K is 1, that means clear, because Q becomes a 0 no matter what. Or sorry, Q plus becomes a 0 no matter what Q was. Then we have the set condition, where J is a 1. J will then set our next state to 1. And then we have the 1, 1 condition, and if you recall in the SR latch this was a forbidden condition, but in the JK flip-flop this is the toggle condition. So this is the condition that then acts just like the T flip-flop, where Q next state becomes whatever Q wasn't, so it toggles Q. If we look at our excitation equation now, remember this is just rearranging this present state next state table into state transitions. So Q going from 0 to 0 will be when J is 0 and it doesn't matter what K is. So if you again look at the table here, Q goes from 0 to 0, J is 0, K is 0. It also goes from 0 to 0 in this case when J is 0 and K is 1. So it's when J is 0 and K don't care. So again, you can then take this excitation table and draw out a state diagram, which we'll just go ahead and do for practice. So this was the T flip-flop. Let's go ahead and draw the JK flip-flop on the next page. So again, we have two states. We have the Q equals 0 state and the Q equals 1 state. And we're going to stay in the Q equals 0 when we have J naught, and it doesn't matter what K is. We're going to go from 0 to 1 when we have a J. We're going to stay in 1 when we have a K naught. And we're going to go from 1 to 0, this is the third row in the truth table, when we have a K. So there's the state diagram for JK flip-flop. And let's again look at a timing diagram. So here we have the clock again, J and K and Q. So remember, we have the hold, the set, the clear, and the toggle condition. And we only evaluate at the edge. So we start off Q at 0. At the edge, we evaluate. J and K are both 1, which is the toggle condition. So whatever Q was, it becomes whatever it isn't. So Q was 0, it becomes a 1. We hold the 1 until the next edge. J is 0 and K is 0, which is the hold condition. So we hold Q as a 1. Because it was a 1 before the edge, it stays a 1. Now evaluate at the next edge. J is 0, K is 1. That's the K for clear condition, so Q becomes 0. Hold 0. At the next edge, J is 1, K is 1. That's the toggle condition, so we go up. We toggle whatever Q was, and we hold the 1. This is J is 1, K is 0. That's the set condition, which means the output is going to be a 1. So that's the JK flip-flop.